Okay, so I'll try to start my talk. So the title of my talk is just reverse mathematics, which is the name of the field, and whose aim is, in a sense, classifying mathematical theorems by way of the logical strengths, I would say. So what is reverse mathematics? People often say that, well, the idea came from Hilbert's reductionism program in 1920s, which says, okay, well, find a good arithmetic system T for the entire math, arithmetic system T in which one can do everything for math, essentially. And then prove the consistency of T by a finitistic method. So you want to find a very strong arithmetic system T and still want to say that it's safe enough in the sense of consistency. But as famously known, this program failed because of Gödel's incompleteness theorem. And then natural question arises. So which axioms are essentially needed for mathematics? I mean, so if you add more axioms, then you may prove more theorems, of course. On the other hand, because you cannot prove the consistency of everything at once, so maybe you should add little by little. So as much as you need to do some part of math. So that's, in one sense, that's the basic idea of reverse mathematics. And Harvey Friedman noticed the following thing in 1970s. So very often, if a mathematical theorem tau, I mean, in ordinary math, is proved from the right axiomatic system, the right axioms, then that statement, that theorem tau itself is equivalent to those axioms over some weaker system in which itself is not provable. Can you all hear me right? I mean, hope it's going smoothly. And let me know if there's some problem. So okay, so based on Friedman's theme, one may classify mathematical theorems by this way, by these ideas. So which is called reverse mathematics program. So the idea is that first, just formalize the theorem tau, or the proof of the theorem tau within an appropriate axiomatic system. And then, okay, let's try to find the weakest axiom T in which we can prove tau, but weakest, hopefully. Then very often, I mean, then one can classify math theorems using the logical strength, using the strength of T, essentially. So that's the idea of reverse math program. So if we first prepare strong enough axiomatic system so that one can develop, redo various types of math. And then, okay, in such a system, we try to identify the weakest axiom for each theorem described in that system. So that's the idea. Okay, for that, well, there are actually many ways to do that. But I mean, in the current most famous setup for that type of research is that using second order arithmetic, which is intended to describe mathematics within here. Omega means the set of natural number, and power set of omega means the and the power set of omega. So many mathematical objects are of course out from here, but still so many things can be embedded into this structure. Structure means that the natural number and a set of natural numbers by coding many objects. Okay, so well, please believe that part. Actually, I can't explain too many details about how to embed more math within this situation. So it's not so. But yes, if we talk about this structure, natural numbers and power set of natural numbers, what type of language is needed? So that's here. So we consider two-sorted first-order logic, essentially, often called second-order arithmetic. Well, second-order means just two-sorted indeed, but I mean, idea is still resemble to second-order logic. So it's two-sorted logic, and then we prepare number and set variables like this, and then constant symbols for numbers, just 0 and 1, because it's intended to describe a system of natural number. And then function symbols is just plus and times. I mean, of course, very basic operators for natural numbers. And then relation symbols. Well, equality, actually for numbers, because equality for sets can be defined as a extensionality, and we don't adopt equality for sets as a basic symbol by the technical reason just. And then order, usual order on natural number, and the element relation between numbers and sets. And then, so now we fix the language L2. So then L2 structure, it's something like this. The pair of M and S, where M is a structure of first order arithmetic. In other words, it is more like a structure of a ordered semi-ring. So of course the natural number itself is an ordered semi-ring. So we would consider various type of ordered semi-ring satisfying the needed axiom, and then consider the power set of that. And of course, we have to prepare needed actions for this language. Well, sorry, but before that, we will consider the classes of formulas, meaning that we try to measure the difficulty of the statement by the complexity of formulas. And the complexity of formulas would be counted in this way. So meaning that, first of all, if a formula in the previous language, like this, only contains quantifiers of the form like this, so they are called bounded quantifiers, then a formula is just called bounded, meaning that there's no quantifier for sets and no unbounded quantifier for numbers. So just formula just contains quantifiers for numbers with this type of thing. So this means that, okay, if you consider this type of quantifier on natural numbers, then, well, the search range is just finite, right? So that's the idea of bounded quantifiers. And then, okay, now we would add more number quantifiers like this, and then that is called sigma n formula. So sigma n formula means that there's a n times alternation of quantifiers exist, well, starting with existential quantifier and exist all n many. And then theta is bounded. That's called sigma 0 n formula. And pi 0 n is just a dual of this. So starting from for all. And analytic formula is, well, now it contains set quantifiers like this. The idea is still the same, but now they are called sigma 1n or pi 1n, and then starting from, so we only count the number of set quantifiers like this, and then now phi is just arithmetical. So any number of quantifiers are allowed in this situation. So this is a class called sigma 1n and pi 1n. And very often we focus on the hierarchy of these type of complexity of formulas. Okay, now axioms for second order arithmetic. So we often consider, well, first several versions of induction. The most basic one is this. So this is an axiom for induction, meaning the phi 0, and for any h, phi h implies phi h plus 1. Then for any natural numbers, phi h holds. That's the idea of induction. So we have to, so because we intended to deal with the natural numbers, so we need this type of axiom. But for the technical reasons, we often display the induction axiom for some complexity of formulas. So sigma ij induction or I sigma ij means that just the induction axioms for all those class of formulas, all those formulas of such a class. And then I delta ij, so delta ij induction is a bit technical. So if some statement is described by sigma ij and pi ij formula at the same time, meaning that for any h, phi of h and psi of h is equivalent, now you can apply the axiom for induction. So that's called delta ij induction. And another version is known as a bounding axiom, b sigma ij, meaning that, or bounding your collection. So for any h smaller than something u, you may find y such as phi of xy. Then, well, if you consider this situation on natural numbers, okay, so for each x, you only find, if you pick some y, and then you only consider u many inputs for this phi of xy, so you can bound all the witnesses. So that's the statement. So this is called bounding. And by same and famous result, actually, so bounding is still considered as a part of induction. Well, actually, delta style induction and the bounding principle is the same. So they are all considered as a version of induction. On the other hand, how can we deal with second order objects? Second order objects means sets. So to deal with sets, of course, we need appropriate axiom for sets, and that's comprehension. So comprehension means, okay, for given a formula phi, well, simply we may say that there is a set x which is defined by phi of x, right? So that's comprehension axiom. And as same as induction, axiom for induction, we may restrict comprehension to some class of formulas. And delta ij comprehension, again, the idea is the same. So if something is provable from, something is described by a sigma ij and pi ij as like this, then you may apply comprehension. So that's delta ij comprehension. And here's a kind of a technical axiom called a weakening of Kenny's lemma, well-known Kenny's lemma, meaning that, okay, for any infinite tree, well, it can be actually described within second order arithmetic, and infinite tree T, well, there is a so-called path of that tree, X, such that X of n is a member of T. So yes. So here, of course, T is considered as a family of all. So this is a family of all 0, 1 sequences. And then, so X is just a set, but if you consider the characteristic function of X, then it can be considered as a function from, this can be considered as a function from natural number to 0 and 1. So h square bracket m means that first n bits of that function. So meaning that the h to the path of t means that for each n, this is a member of T. So that axiom is called weak Keynes lemma. Okay, so these definitions are rather technical, but I mean, so if you are familiar with these kind of discussions, of course, I mean, you may have seen before, or otherwise, just well, I have introduced some kind of a very weak axioms for natural numbers and the set of natural numbers. So now anyway, we can set up so-called the big 5 subsystems of second order arithmetic. Okay, so what are they? So the first system is called RC0, which is okay, which consists of discrete ordered semi-line, axiom for discrete ordered semi-line. Of course, it can be expressed, I mean, described by a given language, and then induction for sigma 01 formulas, and then comprehension for delta 01 situation. Delta 01, well, there's no delta 01 formula, but delta 01 comprehension. And now we would like to add more and more axioms to this base system called RC0. So the second system is known as WK0, which consists of RC0 plus weak Keynes lemma, which I have introduced at the very last part. And then AC0 is RC0 plus sigma 10 comprehension. And today I want to explain the details, but ATR0 fourth system is known as the RC0 plus so-called the axiom for arithmetical transfinite recursion. And then the strongest system, Pi1C0, is RC0 plus Pi1 comprehension. So we will check the strengths. We can try to calculate the strengths of mathematical theorems by comparing with these systems. So that's the idea. And indeed, one may understand these big 5 systems by a more like a intuitive way. So let's say RC0 is just a base system. And in this system, we need to prove everything is computably. So here, the idea of computability comes into this field. Actually, the axiomatic system RC0 is in some sense, it's a natural formalization of a computable math in many sense. And then if you add weak Keynes lemma in such a second level system, one can actually use high-level compactness for example, the closed unit interval of the real line or many compactness situation. And within AC0, now we have a strong enough comprehension to deal with many number quantifiers. So one can essentially use number quantifiers freely, or, well, if you see this system from, for example, the mathematical theorems, then it corresponds to a more like a use of sequential compactness, more like Bolzano-Weierstrass theorem. And within the fourth system, the famous phenomenon is that one can compare well orderings. And in the fifth system, one can check well-foundedness. Here's more like a set-theoretic situation. And if you see from, for example, from the viewpoint of primitive recursion, so primitive recursion is already available within RC0. And all primitive recursive functions are just available within system RC0 and WK0. I mean, in other words, Grushegouzik's hierarchy below omega is just available within RC0 and WK0, but not more in some sense. And then AC0 is essentially the same level as Peano arithmetic PA. So primitive, if you consider hierarchies of functions, then it's usually characterized by epsilon zero. So that's another way of viewing these systems. They are called the more like a proof-theoretic strengths of these systems. Okay, so now we try to do some reverse mathematics. So the reverse mathematics within RCA0 means, well, within RCA0, what kind of math can we do? So within RCA0, one needs to prove everything computably. So, and then indeed, these kind of things can be done within RCA0. The first four things, it seems to be very basic. For example, the nested interval completeness. Yeah, I mean, just the very basic property of real numbers, right? And then with this idea, so this is the essential part of the essential thing provable within RCA0 for reals, and this is enough to prove, for example, the intermediate value theorem or the mean value theorem. And some basic combinatorics is available, and so fundamental theorem algebra is also available, and actually more. So for example, the implicit function theorem or inverse function theorem for like Rn is available. Euclidean space Rn is available, or one can do Taylor's expansion. Well, for C omega functions or like homomorphic function, for example, if you consider complex plane. Or famous Banach's fixed point theorem for contraction mappings on complete metric space is also available within RCA0. Or Jordan curve theorem, known as a bit complicated proof, although it is intuitively natural statement. Well, that's not provable within RCA0 in general, but if you consider piecewise linear Jordan curve, then that's provable within RCA0. And the Bell category theorem is also provable within RCA0. So these are the examples of what kind of things we can do within RCA0. And then the second level WK0 is no, so within WK0 we can do more things essentially. And the key idea is that one can use Heine-Borel compactness of the closed unit interval. And this is actually equivalent to WK0, or Wittgen's lemma over RCA0. And then using that idea, many kind of things are provable within WK0. And actually, to prove all of these things, we essentially need WK0. The uniqueness of algebraic closure of a countable field, or well, so these two are very famous. And so every continuous function on closed unit interval has a maximum. Of course, that's very, very well-known statement. And then it's the proof essentially uses Heine-Borel compactness. And now, and again, the uniform continuity of a continuous function on closed unit interval is also uses Heine-Borel compactness of the closed unit interval, and that's actually also equivalent to WK0. And so many other examples. Brouwer's fixed point theorem, Cauchy-Peano's theorem, Jordan curve theorem. Now it's available within the second system, and Cauchy's integral theorem. Or if you do logic, well, completeness theorem or compactness theorem is also equivalent to the second system WK0. And the third system, SA0, is now within SA0, one may now use sequential compactness. And then with sequential compactness, some stronger theorems are available. For example, the monotone convergence theorem, or like a Algera-Spolis theorem, or the Riemann mapping theorem. Those are equivalent to SA0, as well as other types of axioms. For example, the Ramsey theorem for triples or more, or like every countable vector space has a basis. every countable commutative link has a maximum ideal, and so on. So these things are given to the third system called AC0. And for the fourth and fifth system, actually, so more like a theorems come from set theory or the set theory, or those fields are more comparable to this system. And for example, for the fourth system ATR0, like any two countable well orderings are comparable, that's equivalent to ATR0, or the domain of any Borel function is Borel, or any analytic and co-analytic set is Borel, that's also known as to be equivalent to ATR0, or some kind of determinacy. So Gay-Stewart type of determinacy for open games, that's equivalent to ATR0. And the fifth system, Phi1 CA0, well, Cantor-Bendixson theorem for closed set. I mean, given a closed set on bare space, for example, then it can be decomposed into a countable set and a perfect set. So that's equivalent to Phi1 comprehension, or a bit more complicated determinacy, or sometimes some theorem in analysis. I'll explain this in the last part of this talk, this lecture. So all of these things are known, and they, as you have seen, many theorems can be classified in this way, and many more examples are known. On the other hand, of course, there are a lot of exceptions as well. So these statements are not equivalent to any of the big five. So the originally it's known that so many things are classified into so-called big five, and then people start seeking for exceptions, and now many other type of things are also found. So one very famous one is Ramsey theorem for pairs, or like a countable additivity of the Lebesgue measure kind of a very basic measure theory, or Hilbert's basis theorem for Noetherian ring, or monotone convergence theorem for Lebesgue integral. Well, this actually comes from this idea. And if you know some graph theory, Kruskat's tree theorem is very strong, and while it doesn't imply any type of comprehension, but it's very strong in a sense. Or some stronger version of their category theorem is also not available. All these things are known as exceptions. And then, well, there are more and more exceptions, and nowadays sometimes the situation is known as a reverse math zoo. If you Google reverse math zoo, then you may find this picture in Damir Jaffr's webpage. I mean, it's a reverse math zoo webpage in this. Well, okay, maybe it's not easy to read this, but yes. If you're interested in, please Google, or I mean, search for reverse math zoo. And so now, so we have seen that many classifications, but now, okay, we try to understand the kind of intuitive difference of the classified theorems. Why one theorem is stronger than others? So probably a good way to see it is using some examples, and here we try to consider several different versions of fixed point theorem. So like this. So Banach's fixed point theorem, it's, as I mentioned, it's provable within RCA0. So I would say level 1 theorem, weakest, it's provable within the weakest system. While Brouwer's fixed point theorem is not provable within RCA0, but it's provable within the second level system called WKL0. So why such a difference happens? So well, given any contraction mapping F from closed unit square to itself, if it's a contraction mapping, then it has a fixed point, and it's actually unique. And the important idea is that one can actually computably find such a fixed point. Well, how? Okay, just start from some z, and then calculate f of z, f of z, and f of z, and so on. And then, since f is a contraction mapping, well, this sequence converges, and actually in a computable way, in a computable manner, and the limit is the fixed point, as famously known. On the other hand, for Brouwer's fixed point theorem, okay, if a function f is just continuous mapping, well, not contraction mapping, well, it still has a fixed point. But now there's no computable way to find a fixed point. But still, the existence of a fixed point is supported by Heine-Borel compactness. So that's why, I mean, just essentially, WKL is needed to prove Brouwer's fixed point theorem. I mean, that's not the, I mean, complete reasoning, but still, I mean, one may guess that, okay, Brouwer's fixed point theorem really requires Heine-Borel compactness, and then actually that's provable in some reasonable setting. That's the idea. On the other hand, if you consider so-called Calisti and Kurt's fixed point theorem for solids, Calisti and Kurt's fixed point theorem, that's known as a stronger version of Banach's fixed point theorem. The statement is something like this. On a Polish space means complete separable metric space, Polish space HD, well, if a function C, also known as potential, is lower semi-continuous, so it's a potential type of function from the space H to the positive real numbers. And we may assume that it's a lower semi-continuous. And then consider just any function not need to be continuous, f from H to H. I mean, so it's transformation on H, such that, well, okay, the distance between H and f of H is just smaller than the difference of their potential. So the idea is that if you apply f once, then you would lose this amount of potential. And if you find such a situation, then f has a fixed point. Well, still by way of kind of a not so complicated calculation like this. So, well, let's just consider omega 1 length sequence. So H0 is just any point, and then H alpha is f of H beta if alpha is beta plus 1. And if alpha is a limit ordinal, then just take a limit of all previous things. Then one may verify that X omega 1 is a fixed point. Actually, there is a countable ordinal alpha such that H sub alpha is already a fixed point for F. I mean, it's, but well, yes. But anyway, X omega 1 is definitely large enough. So this is more like a transfinite computation, which is not available within RCA0 or WK0, or not even in ACA0, but within ATL0, you may deal with more like a transfinite recursion type of thing. So you can now consider this kind of idea. Well, actually, but still, so Calisti-Kirk's fixed point theorem is indeed stronger than ATL0, and it's provable within Pi1 comprehension. And well, it's still open whether it's actually equivalent to ATL0 or not. That's this is more like a newer result, so still some part is open, actually. But anyway, we may see the difference of these four fixed point theorems. So this kind of difference may be may imply some more like a, for example, a concrete difference for the existence of, so this theorems in PDE. Well, this is actually ODE, but differential equation. So for example, the Banach's fixed point theorem implies the Picard's theorem for ordinary differential equation. Let's say if f is a Lipschitz continuous function on this situation, then the initial value problem of this form, also of course there should be a of course this is like this, f of x, y, and what I meant this. So dy of dx is f of xy, which is Lipschitz continuous, and then the initial value is just 0, has a solution on this interval, and that solution is obtained essentially by Banach's fixed point theorem. So this is probable within LC0, while the Cauchy Peano's existence theorem, so essentially the same assumption, but just continuous. Now you need a more like generalization of Brouwer's fixed point theorem, also known as Schauder's fixed point theorem or Capitani's fixed point theorem. And with those things, one may show that this type of differential equation has a solution. And indeed, this difference can be considered as a difference of the strengths of computability. So in the first case, well, any f has a unique computable solution. While in the second situation, any computable f and any PA degree, well, if you know something about the computability theory, a degree which computes a completion of Peano arithmetic D, well, such D computes a solution for f. And on the other hand, there's a special computable continuous function f such that any solution for f has to compute a PA degree. So that's the reason why Peano's existence theorem is equivalent to WK0 over C0. So in other words, so the strengths of mathematical theorems can be captured by the strengths of computability in a sense by using this type of analysis. So in general, what we have seen for that idea. So as I mentioned, the setting of reverse math is for the study of the structure of the form natural numbers and the family of sets of natural numbers. And so if S is just the same as the power set of omega, that's the kind of a full situation. But if we only assume weaker axioms, then S may be smaller than power set of omega because of the lack of comprehension axiom. Well, so indeed, some famous ideas of computability theory can be, some ideas of computability theory corresponds to the models of big five systems. So more precisely, well, S is a Turing ideal, meaning that if a family of sets of natural number is closed under Turing reducibility and usual join, if and only if it's a model of, it consists a model of, it forms a model of RCA0. And if S is known as S forms a Scott ideal, I mean it is Turing ideal closed under taking relativized PA decree. I mean, if you know something about it, that captures the second level WJ0. And if S is a Turing ideal, which is closed under jump operator, then it characterizes a model of SCA0. So all these things are defined by using the idea of basic computability. And so one can consider the difference of these systems as the difference of the strengths in the sense of computability. And indeed, well, if you want to know more detailed difference, more precise scale, well, probably doing analysis within second order analysis is not quite appropriate. And then you may consider some more like purely computability theoretic approach. Recently, the study of Weyrach decrees are quite popular. And there's a big success on comparing various types of mathematical theorems. Well, on the other hand, if you do strength analysis within second order arithmetic, one may also capture different type of strengths known as the induction strength or proof-theoretic strength. So for example, we may prove these things within RCA0. So the infinite pigeonhole principle, which is a kind of a simple infinitary combinatorics, is indeed equivalent to the delta 1, delta 02 level induction axiom. So the pigeonhole principle is actually considered as a form of induction, actually. And so because induction, it's just a statement on natural numbers, it never implies comprehension. So we may have no extra sets stronger than RCA0, but still we may have a stronger induction. That's the idea. So infinite pigeonhole principle, that does not require stronger induction, stronger comprehension, but just require stronger induction. And if you do some like a study of automata theory, one good example is that complement tension theorem for Buffy automata, if you know such a statement. It's equivalent to sigma 2 induction. So I sigma 02 is slightly stronger than I delta 02. And the famous Hilbert basis theorem for Hilbert basis theorem in algebra, for Noetherian rings, that's equivalent to well-orderedness of the ordinal omega to omega. So some ordinal alpha is well-founded. That can be also an axiom. And those things are always provable from kind of a strong enough induction in a sense. So this also gives a new type of characterization of mathematical theorem. So Hilbert's basis theorem, still okay. It's not trivial. It's not provable within RCA0. Well, actually known as even not provable within WJ0. But if you add some stronger induction or well-foundedness of some small ordinals, that's enough to prove the Hilbert's basis theorem. And Robson's basis theorem, it requires actually a bit stronger ordinal. And if you know graph minor theorem, well, actually this requires a huge induction or huge well-orderedness principle for ordinals, which already implies consistency of the strongest big 5 system called Pi1 comprehension. So graph minor theorem is a known as very difficult theorem, but actually you may also verify the this theorem is very hard in the sense of proof theory. Well, that's famous Friedman's result, or Friedman, Robertson, and Simon's result. Well, so all these 5 statements are true in any omega model of RCA zero, in a sense. Oh, sorry. So, no, yes. Any omega model of RCA zero. Meaning that, okay, computability theory cannot distinguish the difference of these things. So what's the key? So that's consistency strength or prosthetic strength or first-order strength. So which is based on the hierarchy of primitive recursive ordinals, such as, well, omega is probably the smallest infinite ordinal here, and then omega to the omega, omega to the omega to the omega, and so on. And if you repeat this process, you may reach epsilon zero, and then epsilon zero, epsilon sub epsilon zero, and so on. You may reach bigger and bigger ordinals, and gamma zero is known as the bigger ordinals than these things, and so on. And well, now this hierarchy corresponds to the strength of consistency, for example. So this second level ordinal, omega to omega, corresponds to roughly speaking, it corresponds to the consistency strength of RC0 or WJ0, first 2 systems. So this implies the consistency of RC0 and WJ0. While, so by gated completeness theorem, RC0 or WJ0 cannot prove the well-orderedness of omega to omega. And well-orderedness of epsilon 0 implies the consistency of ACA 0, and gamma 0 implies the consistency of ATR 0, and so on. So by the way, the mathematics below the level of omega to omega, so let's say the level of WJ 0, may be considered as a partial realization of Hilbert's reductionism program. Well, I won't talk about much now, but I mean, if you're interested in, there's a famous survey by Simpson, so that's, well, good to know. Yeah, I mean, and so these things are traditionally more like known as a purely proof theory type of things. But nowadays, in the recent research, by the recent researches by various people, well, I just mentioned Fround here, but many others, Fedor Pakmov, Anton Fround, Juan Aguilera, of course, Andreas Weiermann, Michael Bastian, those people now developed more like a concrete correspondence of this type of well-orderedness principle and systems of reverse math, even with a comprehension. So I mentioned that this kind of thing never implies comprehension. Well, in a traditional sense, well, this well-orderedness never implies comprehension. But if you consider more like relations between these things, then one may reduce stronger comprehension. And this kind of hierarchy also corresponds to the hierarchy of induction, especially below the level of ACA 0, which is known as Kirby and Torres hierarchy, and of the form something like this. So sigma 01 induction actually corresponds to the level of RCA 0 and WJ 0. And this is D sigma 2 or I delta 2, and I sigma 2 is strictly stronger, I delta 3 is strictly stronger, and so on. Okay, and then below the level of ACA 0, a famous study of a calibration of mathematical theorem is about Ramsey's theorem. And so let's say RT and K Ramsey itself of n tuples and K colors is a statement that for any infinite set of natural number and for any so-called coloring from n tuples of from H to K, there exists an infinite set H such that, well, P is constant on any n tuples from H. So that's known as infinite Ramsey theorem. And RTN is simply for any number of colors, K, RTN K holds. And then, well, the hierarchy of Ramsey theorem known as like this. So RT12 is essentially just a simple pigeonhole principle. Okay, if you split a set of natural numbers into two parts, then one of them is infinite. That's RT12. And RT1 is essentially the same thing, but arbitrarily finitely many split-ins. So that's still easy statement. And then the first non-trivial Ramsey type statement is RT22, and the RT2 is strictly stronger than that, and RT32 is now equivalent to ACA0. Well, on the other hand, RT22 is in a sense tricky, and it's not equivalent to WJ0. Actually, it's incomparable with WJ0, and it's strictly in between RCA0 and ACA0. And if you see the computability theoretic strengths, so the first two things are computably trivial, and second two things are, well, from the computability theory, just the same thing, because this is just requires just stronger induction. And then Ramsey itself of triples just equivalent to the third level arithmetical thing, the level of ACA0. So this is actually the Turing ideals closed under jump operator. And so if you see the computability theoretic strengths, okay, this is trivial, this is the second level, this is the third level. While on the other hand, if you consider the strengths in the sense of consistency, then the behavior is different. So the first three things are the same. So now these three things requires the same level of induction. While the fourth thing implies stronger induction, and then RT32 is strictly stronger than that. And if you check the strength of induction directly, then okay, meaning that compare with Kirby-Paris hierarchy, then the first level is I sigma 1. Second level is actually I delta 02. And the third level is still open. I mean, it's a very long open question. Maybe equivalent to I delta 02 level, but it's still unknown. And the fourth stage is I delta 03, and the RT3 is just the level of PA. So using second order setting of the second order arithmetic, we may consider the strengths of, for example, Ramsey's theorem using two different type of measures or three different types of measures. So that's, I would say, an example of two-dimensional calculation of classifying mathematical theorems. And is that all to calculate is that all for classifying mathematical theorems by using logic? Well, of course, there are plenty of other different ways. And one famous one is, well, focusing on the strengths of excluded middle or like uniformity. So for example, Banach fixed point theorem and the intermediate value theorem and RT12, Ramsey itself of singleton and two colors, are all provable within RCA0. But if you consider just these things sequentially, then there's a difference. So for example, sequential version of Banach's fixed point theorem says that, okay, given a sequence of contraction mappings on Z1 unit Q, then there's a sequence of fixed points. This is still provable within LCSL. But if you have a sequence of continuous function on closed unit intervals such that F0 times F1 is negative, then, of course, by intermediate value theorem, there should exist a sequence of numbers such that f of AI is 0. So sequential solution in the sense of intermediate value theorem. But that's not provable within LCSL, and it goes up to the second level WKSL. And if you do the same thing for just very simple Ramsey's theorem, RT1, 2, then it goes up to the level of ACSL, the third level system. So why this happens? So this comes from the non-trivial use of excluded middle non-uniformity. And then, well, why this is not blue? I mean, I would say, okay, this is also very important. And then for this type of, to understand this type of difference, well, okay, probably the current setting of second-order arithmetic is not enough again. And then various other type of study might be more appropriate. So for the strength of excluded middle, the study or some other types of, or many other types of logical axioms, which is available within classical logic, but not in intuitionistic logic. Those type of studies known as constructive reverse mathematics. And then you can also study the difference of these things from the viewpoint of uniformity. That's also known as study of prior degrees. But sorry, I mean, today I won't mention more about these type of studies. I'm not a specialist of those fields either. Okay, so I would say, what about other type of questions? So what's for future studies or what's the ongoing studies? So, for example, we have seen various types of mathematical theorems in the setting of second-order arithmetic, but they are mostly more like a, well, roughly speaking, mathematics studied in undergraduate course level. So how about, or maybe graduate levels, many of them are still graduate levels, but not kind of a ongoing research levels in other fields, I would say. So what would happen if we consider more like difficult math theorems? And then do they require stronger axioms than, for example, Big Five? Well, it's actually very hard to say, but I mean, one of the future studies should go that direction, I think. On the other hand, of course, the knowledge of the logicians are kind of limited in many situations, so it's not easy. I mean, so to do this kind of thing, of course, one has to be a specialist of logic and other fields. So that's not so easy, but I hope this type of results would appear in the future, not so far in the future. And we have introduced several different types of scales. I mean, computability theoretic strength, proof theoretic strength, and so on. Then how they are related. So we need some more modern frameworks for that kind of ideas, I would say. So are these things available? Or like, we can also consider some new or different types of scales. And one I would say that seems to be interesting is well, what happens if you consider using the scales, something like length of proofs or size of proofs and so on? But this is actually so hard to calibrate, so we need another new type of new ideas. But I mean, yeah, it should be interesting. And how the different frameworks are related. So actually, these things are more like my recent motivation. Well, for the first one, actually, I'm not good enough to do this kind of thing, but I'm generally thinking about kind of a more kind of a rare type examples or like a general frameworks to this situation. So in other words, seeking for a better way to calibrate or classify mathematical theorems. And here I would introduce a few results of that direction from my recent studies with many of my colleagues. Sorry, I haven't mentioned the co-author's name here. It's not great. So the first examples is that this is a very tricky theorem, but it's very interesting actually. The entanglement of scales also. Sorry, I have a phone call. I'm so sorry. I mean, I'm talking from my office and there's a phone call and I can't stop it. I'm so sorry. Well, okay. So here's the theorem about some kind of entanglement of different type of scales. Actually, the entanglement of a strong strength of induction and computability. So the theorem says like this. So if the second order structure M and S is a model of RCA0 plus I delta 0 M plus 1, but not I sigma M plus 1. So it has some induction, but not the next level. And then in that structure, actually, there is a special element A whose jump is just limited. And compute everything in S. So what's that? So okay. So okay, if you find a special element A, that M of A is a model of I delta 0 M plus 1, and this is actually PAD relative to 0 n jump. I mean, nth jump of A is a PAD relative to nth jump of 0. Then there exists the S tilde power set of M, such that for every h in S tilde is sigma A M plus 1 definable in M. So everything is definable. And this is isomorphic to the original model. So roughly speaking, any elements in S should be always computed from a single element, should be definable from single element in a fixed level. So meaning that very roughly speaking, okay, with the limited induction, there exists a single element A such that any inductive set on M should be definable, I mean computable within some jump of A. Meaning that computation with M plus 1 jump never be available within this system. Or I mean, or no undefinable object are available within this system. So this restriction of induction strictly restrict the strength of computation as well in special setting. So in other words, I mean, the strengths of computability and induction more or less connected. And the connection and the revealing the connection between them is still seems to be important research. So that's one thing I'll try to mention. By the way, this is solely, I mean, I should write the quarters. So this is with a theory coronas. Ecologic. One and myself. This is a one new interesting result related to this kind of topic, I think. And another one is a example of kind of a concrete analysis type of result, theorem, which requires stronger axiom. So within the fourth level, fifth level reverse math, well, the theorems equivalent to the fourth level, fifth level axiom were mostly related to set theory kind of thing. But actually, there should exist some more like a theorems in concrete analysis, I mean, analysis type of statement. And here's maybe a first example of that such kind, known as Ekland's variational principle. And what's that? So let's say HD be a Polish space, and then given 2 points x and y, well, x is weaker than y if the distance between x and y is smaller than f of y minus f of x. So I would say one may move from y to x. So if we consider f as a potential, and then okay, distance between x and y is smaller than the difference of potential. So this is more, and this forms an order relation. And then a point x is said to be pseudo minimum, a critical point, if it is a local minimum with respect to this theorem. And then Ekland's theorem says that for any lower semi-continuous function on a Polish space, and for any point h0, there is a pseudo minimum, or such that actually reachable from h0. So this is still more like a theorems in an abstract setting, but actually, if you consider Ekland's theorem on the space of continuous functions on closed unit interval, well, this version of Ekland's theorem is often used for a optimization problems or like PDEs. Actually, to be honest, I don't know much about the real examples, but I heard about it. And then and then still, it is equivalent to Python comprehension. So from this result, maybe there's a more concrete question problem in PDE, which already requires Python comprehension. So solving this differential equation, well, okay, that's possible, but you have to use pattern comprehension, which is very strong axiom in the sense of reverse math. So the current known thing for PDE is, well, if you find a solution, if you can always find a solution, then that thing is provable within mostly at the level of ACSL. But perhaps there may be a kind of a stronger example that to solve this differential equation or to solve this type of differential equation, okay, you may prove the existence theorem for the solution of the solution, but you need a stronger axiom. That situation might happen. I'm very much interested in those examples. Okay, so that's all essentially about the kind of a contents in the to introduce reverse mathematics. And since I still have some time, I'll try to show some very basic ideas of the equivalent proof. For example, the so this thing. So the over RCA0, well, as I mentioned, well, WK0, the second system is equivalent to the statement that any continuous function on Cantor space, which is known as a compact space, has a maximum, or any continuous function on closed unit interval has a maximum. This is equivalent to WK0, very well-known result, but I mean, I'll try to give a brief idea of the proof, and also the more recent ones. So the pi1 CA0 is equivalent to the Ekman theorem. Well, let's say on bare space. So we should continue the contents, and actually, so in this latter half, well, actually, for I would say I'll try to talk a bit more about a kind of to introduce very basic idea, the proof that how to show that some mathematical statement implies more like axiom. For example, we change lemma and so on. So here, the theorem I've already mentioned in the very earlier slides, saying that the over RCA0, well, the statement that any infinite tree has an infinite path, which is known as Wittgen's lemma, this is a combinatorial statement, is equivalent to the statement that any continuous function on bare space has a maximum. And actually the same thing on the closed unit interval. So how can we show this kind of thing? We'll see the very basic idea. So, well, actually, I'll essentially just show the one direction. But so first, 1 implies 2 and 3. This is essentially come from by Heine-Borel compactness. So it's just essentially the same as usual idea. So with double KL, with Wittgen's lemma, Heine-Borel compactness for closed unit interval or Cantor space is available. And then, well, by compactness, any continuous function on such a space has a maximum by the usual argument. So if you can carefully formalize those proofs, then you may have a proof of 1 from 2 and 3. But the converse direction, so reversal, 2 implies 1, we need to consider more like exotic situation. Because I mean, we want to prove a axiom from mathematical theorem. And so the idea of the implication of two to 1 is the following. First of all, it's known that within LCA0 proves the following thing. So if f of n is a sequence of continuous function on the Cantor space or on closed interval such that the matrix of f of n, if it exists, is bounded by, let's say, 2 to the minus n, then the sum of all these functions exists as a continuous function. And that's provable within LCA0. So this is, of course, by an easy calculation, this is just a uniform convergence, right? I mean, limit of a uniform convergence series of continuous function. And that's kind of well-known result in LCA0. And we'll try to use this. And now what we need to prove from 2 to 1. Well, actually, we will show the negation of 1 implies the negation of 2. So, okay, let's say, let's assume that the negation of this holds. So there is an infinite tree T which doesn't have an infinite path. So let's say T is a binary tree which is infinite, but T has no infinite path. Then what happens? So define T circle. This is not a tree actually. A family of leaves. So binary sequence sigma in 2 to the S and M such that sigma is not a member of T, but sigma minus is a member of T, and sigma minus, where sigma minus is at T. Just cut off the last element of sigma. So just one shorter, cutting off the last bit of sigma. So that's sigma minus. Then we may check that for any element in bare space, Cantor space, 2 to the n, 2 to the n means, of course, the function from natural number to 0, 1. There is unique sigma in T circle such that H is an extension of sigma. This, of course, comes from the fact that T has no infinite path. Because T has no infinite path, hence X restricted to some n has to be out of T for some n, right? So because of this reason, So given any x, well, that unique sigma such that sigma extends x, then sigma itself is not in T, and just the first one getting out from T. So now we define f from the bare space to real number as, so let's say fn, f sub n. Fn x is just the 2 to the minus n if x extends sigma for some sigma in T circle such that, and the length of sigma is just m, and 0 otherwise. So because note that the often like the sigma square bracket then h such that h in Cantor space such that sigma h extends sigma is a Klopen set of the Cantor space. So hence fn is of course continuous function, and easily computable. Hence it's available within Alcézil. It's very simple function. So just because there's only 2 to the m many lengths and secants, so checking whether x extends sigma, which is in a member of T circle or not, can be easily verified. So just compute the first m bits of x and check whether it's in T circle or not. That's all. So that's computable then, and that defines in continuous function. Of course, the value is just the same on each Klopen set, and the space, the whole space, the Cantor space is just divided into 2 to the m many Klopen sets. So it's of course a continuous function. But now, if we take a sum of all these functions, let's define f is just the sum of all these, and this is still from the Cantor space to real numbers. So it's a uniform convergence limit of a continuous function. So this is of course continuous function. Available within. In Alcézil. But however, this f does not have a maximum. Why? So, okay, if a value y attains the maximum, well, okay. So f of y has to be some 2 to the minus n or some sigma in T circle such that y extends sigma. However, I wanted to say assume that this n. However, since T is infinite, T circle is also infinite. So there has to be tau in T circle such that the length of tau is bigger than length of sigma. And on the other hand, z equal tau concatenated with many ones, for example, zeros or ones, so it's essentially the same. F of z, so this is of course a member of Cantor space. F of z is 2 to the minus length of tau, which is bigger than f of y. So y can't be the maximum. So that's the reason why this f doesn't have a maximum. So indeed, a picture is something like a, so you may consider tree with no infinite path. Then, so tree is infinite, so there's always a longer. So if this is T, then okay, T circle is something like this. And these points covers the whole Cantor space covered by open set generated by T circle. So the value of f is always bounded by one of them. One of the T circle, I meant this is actually not this, 2 to the minus the length of sigma. But this is infinite. This is infinite, so f doesn't have a max. That's the idea. So very roughly speaking, if it's something like so the value of f is something like this. Well, just very vague idea. And one can actually smoothen the previous construction, and then we may get a continuous function on closed unit interval, which doesn't have a maximum, assuming the negation of WK0. So that's the reason why 2 implies 1 and 3 implies 1. Okay. And then, yeah, we may also consider kind of a similar type of discussion for much stronger situation. So this is now the more like a recently known equivalence about the comprehension. So namely, Python comprehension is equivalent to Eklan's theorem on bare space, saying that any lower semi-continuous function on bare space, lower semi-continuous function which is positive on bare space has a pseudo minimum. So that is equivalent to the Python comprehension. And to show that, actually, we will use the characterization of Python comprehension, saying that, okay, Python comprehension is just equivalent over RCA0, that the statement that for any sequence of trees, there exists a set H such that, well, H knows which trees which trees have a path. I mean, so I is a member of H if and only if Ti has a path. So this is equivalent to Python comprehension. And I've tried to show the idea of how 3 implies 1. In other words, why Eklan's theorem on bare space implies the Python comprehension. So to see this proof, well, okay. So we want to show that, so given a sequence of trees, more like a bare space situation like this, we want to construct a continuous function, a lower semi-continuous function, whose pseudo minimum would compute this kind of edge. That's what we want. So to show 3 implies 1, let's say Ti is a sequence of 3. Oh, by the way, so it's known that, so I mentioned here over RCA0, but actually I would like to work within SCA0 because it's not so difficult to check that 3 implies SCA0. But I mean, I'll just omit that part and then just focus on the kind of a core part of the proof. So let's say, Ti is a sequence of trees. So now, well, just consider standard pairing function, and given a given H, the member of bare space, I mean function from natural numbers to natural numbers, I'll try to consider ith component of H sub I. This is also a member of bare space such that, so H I n is just the H of In, where this is a standard pairing function. So using the standard pairing function, you can consider a member of the bare space. It's just a sequence of members of bare space by the usual pairing function. So just the easy rephrase. And then we would like to define a lower semi-continuous function f as follows. So first we define Fi from bare space to actually just 0, 1 as follows. So Fi of x is 1 if ith component of x is not a path of Ti and 0 otherwise. So here, to check that x sub I is not is a path of Ti or not. So this is actually a path of all passes of Ti. I mean, square bracket Ti means just path of Ti. And then checking that it can't be done in a computable way, but still this function can be considered as a lower semi-continuous function because so this Fix it's actually a limit of increasing limit of Fin of x, where Fin of x, just saying again, just 0 and 1, if x sub I restricted to n, it's not a member of Ti whose range is smaller than just n. So this is just easily checked, just calculating n speed of h sub I. So that's easy. And well, okay, we don't need this, just not in Ti. So this is easily checked. And so Fin, these things are continuous function. So Fi is a lower semi-continuous. And it's available within in AC0. Well, unfortunately, not us. Well, maybe even within AC0, but we don't care about it. And then now we can consider F from bare space to the real or positive real, saying that simply F of x is the sum of Fix. Well, let's say, 2 to the minus I times Fix. So this is still lower semi-continuous function on the bare space. Well, so okay. So Ekman's theorem says that any lower semi-continuous function on bare space has a pseudo minimum. So let's say H star is a pseudo minimum for F. Well, what was the definition of pseudo minimum? I mean, it's not so easy to remember. So the idea is that, in other words, for any y in the bare space, if what's that? The distance between h star and y, distance in the sense of bare space, of course, the usual bare space, it's smaller than f of h star minus f of y, then y has to be equal to h star. So that's pseudo minimum. So from h star, any point around h star, well, moving to that point is impossible in the sense that if you move to h star, any point near h star, well, the distance between h star and y is bigger than the difference of the potential between them. So that's the idea of pseudo minimum. So within this situation, we may compute the set H, judging whether Ti has a path or not. And such an H is easily defined as follows. So let's define H as the set I, such that I's component of H star is a path of Ti. So this set H is available by arithmetical comprehension within HCA0. And we want to say that I is a member of X if and only if Ti has a path. Well, okay. So because H star I, so I is just a collection of all things that H star I is a path of Ti. So of course, if I is in X, then H star I is a path of Ti. So of course, this relation is trivially true. We want to check the inverse direction. So if I is not a member of X, and assume that Ti still has a path, then what happens? So because H star I is not a path of Ti, but there is, since Ti has a path, so let's say Y is a path of Ti. Path of Ti. And then we may define Z a new member of Bear space so that G sub I is G sub J, so I is fixed. I is fixed here. So G sub J is just H star J if J is not the same as I, and Y if J is I. So this is a new member of the Bear space. But then distance between H star and Z is smaller than actually the first bit of the difference has to be I, meaning the 2 to the minus the pairing function of I and 0. And by the usual calculation of pairing, usual thing of pairing function, this is of course smaller than 2 to the minus I. But by the definition of F, the definition of F is something like this, where so Fi is just true if a H star I is a path of Ti. So this is just the same as F of H star minus F of Z, which is a contradiction because H star is a pseudo minimum. So if this condition holds, then Z has to be identical to H star. But of course, this is different on I's component. So it's a contradiction. Meaning that, if I is not a member of X, then Ti doesn't have a path. So that's all the proof. And we have seen that Ekland theorem on bare space implies final comprehension. Okay, so that's a kind of these are typical examples how to prove the mathematical, how to prove the axioms from some mathematical theorems. Okay, that's all of my lecture. Thank you very much.